Okay, I guess you can start now. Hello, everyone. My name is Mete Atamel. In the session note, in the agenda for the conference, it says Atamel Mete, but that's not my first name. My first name is Mete, actually. So I'm a developer advocate at Google. I'm based in London, and it's my first time in Singapore. It's a great city. I'm very happy to be here. I'm a little bit jet lagged, but hopefully it won't affect my presentation. All right, so today we're going to talk about microservices with Kubernetes. So in my presentations, I like to give you the whole topic up front. So let's just do that from the beginning so you know what you're signing up for. So I think software development is hard. I mean, who agrees with me? Like, does anyone think that software development is easy? I don't think so. And the bad news is that it's not getting any easier. If you look at all the developments in software development, we have all these tools and frameworks and languages and all this kind of stuff that you would think make things easier for us. But if you think about it, it's actually getting harder and harder. But the good news is there are frameworks and tools like Kubernetes that can help. So this is the whole point of this presentation. I will basically go through about software development, why I think it's hard, and then we're going to go through containers, how they help, and where they fall short. And then we're going to look at Kubernetes, what it's trying to do at the high level, and then we'll take a look at Kubernetes building blocks like one by one, and then we'll see how it can actually help with the craziness in software development today. So that's the whole talk. Hopefully this is what you sign up for. If not, feel free to go, but hopefully stay. All right, so a little bit of information about myself. As I mentioned, I'm a developer advocate at Google. I'm based in London. This is my Twitter and my email. I already have these slides up on my Twitter account, so if you want the slides, just follow me, and there should be a link there. And also, if you have any questions about any of the stuff I say today, you can find me after my talk, but you can also always email me from this email account. I also like to get feedback about my talk, so I have a feedback link, bit.ly/my last name. If you fill it before the end of the session, or right after, I have 3 T-shirts that I'm going to give out to people who filled it. It's the first 3 people. But then I also have some stickers, Google Cloud stickers, so even if you don't get a T-shirt, feel free to stop by for the sticker after the talk. All right, so let's get started. So anyone recognizes these? Anyone worked with these before? Yeah? Okay, good. It's always a good feeling that I'm not the only guy who worked on these, so I'm not the oldest one here. So in the good old days, when I started programming, I didn't use the biggest ones. I used the ones in the middle. That's what I started using. So I used to have this MS-DOS disk. I would put it in my computer, floppy drive, close it, turn the computer on. The computer would boot. Then eventually I would get the A drive, and then from there I would take it out. I would put the other disk. It was, I think, GW Basic or Q Basic, one of them. I don't remember. It was so long. And then I would just start programming. And if you think about it, this was like the only thing I had to care about, right? You know, in microservices, they have this notion of bounded context. Like, this was my bounded context. It was really bounded, right? You couldn't escape from that. So all I had was this disk and a book on QBasic, and it was really fun. Like, I would just sit hours and hours and trying to hack things together. Of course, it wasn't always fun. Sometimes I would get stuck, and there was no internet, there was no Stack Overflow, so I would spend days trying to figure things out. But that simplicity was really fun. Since then, a lot of things happen, actually. The first thing is obviously internet. And then from the internet, we had all these other things. Like, we had app servers, databases, machine learning, big data, IoT, cloud computing, mobile. It's like so much, right? So it's really impossible to know everything in detail. So what I try to do, and I am sure it's the same for you, is pick and choose what you like, and then try to focus on a few things, but then at the same time try to get a good overview of what's out there so that in case you need to do something in other fields, you have an idea of what to do. So nowadays, if you want to solve a problem, you still write the code. So let's just imagine that this is our code. By the way, I'm totally ignoring this because it's so far out. So I'm sorry for that, but that's how it's going to be because I will try to remember, but it won't happen. So nowadays, if you want to solve a problem, you write your code. So let's just imagine that this is our code. And it's not on a disk anymore, so you need to deploy it somewhere. So you find a machine. It can be your own machine, or it can be your data center, or it can be somewhere in the cloud. So your code gets deployed. It's not that complicated. It's great. It's running. But then someone says, what happens if this machine goes down, right? You can't just rely on a single machine. So what you do is you take the same code and deploy to multiple machines. So if one of them goes down, you still have your other machines working, right? But then the problem is, how do your clients get to your machines? They cannot know all the IP addresses. So you need some kind of load balancer in front of them, right? So the load balancer has the static IP, and the clients connect to load balancer, and then from there you use some kind of load balancing algorithm to reach to the machines. That's great. But then what happens, like how do you even know these machines are working? You know, just because they're online, it doesn't mean that your app is running. So you probably need some kind of health endpoint on these machines. So you create a health endpoint where you check certain things about your application, see and make sure that your app is actually running, and then if it's running, you say okay, and if it's not running, then you say not okay. So that way you know if your app is healthy or not. But you know, creating this health endpoint is not enough. You need to actually have something checking that endpoint. So what you end up doing is you probably create something called like a health checker. You either create that yourself or you rely on your cloud provider. Basically just pings your health endpoints and make sure that your app is running. And then maybe additionally, if your app is not running, it might bring down the machine and create a new machine and make sure that it's healthy. So this health checker, it checks for the health, and it also provisions the new machines if something is not healthy in one of the machines. So that's great, everything is working, but this whole thing is in one zone, in one data center. And even with cloud providers, sometimes the whole zone goes down. So what do? You create the whole thing in a different zone with the whole setup in a different zone, just in case something goes wrong with this zone, you can switch to another one, right? Now you have another problem. You have some kind of state here, and then you need to make sure that state actually gets replicated to the other zone, right? So what you usually do is you have something in the middle. It's usually some kind of a task queue where when you write stuff here, you put it in a queue, and then this guy pulls it from the queue. So that way, the state of one zone gets replicated to the other zone. So that's great. I have two zones. They're in sync for most of the time. That's great. What if your application is kind of successful and you need to scale up? You can scale up manually, but then what if, sometimes your app is cyclic, so during the day you have lots of users, but then at night you don't have that many users, so you need to scale up and down constantly. So it's hard to do manually. So what you usually do is you use an autoscaler. So you either write yourself an autoscaler or you rely on someone else's autoscaler. But basically it looks at your usage, how many people are using your app, and it scales up and down depending on that, right? So our little app all of a sudden got quite complicated. And we haven't even talked about having different languages and different types of machines. So we are talking about a single code running on a single type of machine. But if you need to do multiple languages and multiple different kinds of machines, this gets even more complicated. When you want to deploy a new version of your application, you need to think about it because it's not just one machine and one code, right? It's on multiple places in multiple zones, so rolling that out in a reliable way, it's not that easy anymore. Let's say you want to roll your new version, but there's something wrong with it. You need to roll back to the previous version. That becomes complicated. Then your configuration and secrets, right? So your code is one thing, but the configuration of your application and the secrets of your application, like passwords and stuff like that, that also needs some kind of management, and you need to think about that. And then finally, the scripts. Every time your machines start, they usually has some kind of runtime startup scripts that needs to run. So you need to manage those as well. As your code, you need to also manage your scripts. So there's all this other stuff that we didn't even talk about yet. So at this point, if you're like me, you're kind of like this guy, because I am an application developer. I like to solve real-world problems. I don't want to really deal with this kind of operations, right? These are kind of distracting me away from what I need to solve. So I kind of feel like this guy sometimes. So the reality today is that this is what I want to care about. This is what I want to work on, the actual code. But in the end, I end up caring about the whole thing with all the replication and health checks and autoscaler, things like that. And actually, I worked at a place once where the ratio of coding versus operations got so bad that I actually quit the job because I was spending most of my time trying to manage all of this rather than coding. So that ratio has to be maintained carefully. Otherwise, developers don't like to do just that, right? So what do we do in this case? Now, in the good old days, not so long ago actually, I would write my code and then I would just pass it to QA guys and say, can you please test this for me? Because as a developer, I don't do tests, right? We are software engineers, we don't do tests. And let them do the testing for me. And then we would fight back and forth. They will send me a bug, I'll argue with them that it's not a bug, and then they will send it back. Eventually I fix it, and then once everything is bug-free, then I pass it to operations people and say, can you just take this and run it in operations, in production? Because I don't know how to run stuff in production. I'm a software engineer, I'm not an operations guy, right? And he would figure out all these details, and I would just take this approach over, it's not my problem, let them test it, let them run it, I just write my code. And to be honest, I think it kind of felt good because I was just doing the fun part, and then the hard part was done by other people. But in reality, it wasn't good practice because I wasn't getting, and I think it was same for most of you guys probably before DevOps, is that I wasn't getting the feedback I need to build resilient applications. Then the notion of DevOps came along. So the idea in DevOps, as most of you know, is that as a developer, you're responsible from beginning to the end. So you write the code, you test the code, you run it in production. If it needs fixing, you go and fix it, you deploy it again. So this way you basically do the whole thing, and as a result, that makes you write code that's more resilient, and it really helps. I have to pause here for a second. So when DevOps implemented correctly, it actually helps, but I've seen places where DevOps is not done correctly, where people just use DevOps as an excuse to just ship code without really testing it properly, without really putting automation properly. In those cases, actually DevOps kind of like blows up, and then you have people quitting jobs because everything is so not maintainable. So you have to do it carefully. So what do we do? So if I have to actually imagine how software development should be, there are a few things that I want to happen. So the first thing is, I want to be able to write code in any language I want. I don't want to be constrained by one language or one environment. And I want that code to run anywhere in the exact same way I specify on my laptop. I think this is really important. I want to make sure that whatever I write on my laptop, the way it works here, it should work the same way everywhere, because it's really important to have the context everywhere. The second thing is, I want to, take my code and optimally deploy it somewhere. So I want someone to basically look at my code and say, okay, let's just deploy this on this machine because that's the machine that's free. I don't need to worry about that kind of stuff. Someone has to figure that out for me and just deploy it optimally somewhere for me. As a developer, I shouldn't really care about that kind of stuff too much. And the third thing is, there shouldn't be even machines. All the resources that I need should be automatically provisioned and available to me on demand. Because in this world, we have demand coming in and going all the time. So I want things to be elastic. I want machines to be added and machines to be removed as I need them, right? So if I have these things, I think we're on the right track. And if you look at what happened in the last few years, we are kind of getting there. So if you look at the first claim, writing your code in any language and running it anywhere exactly the same way, well, that's what containers are all about. So if you look at Docker and the other container platform Rocket, they are basically trying to create this notion of context that you can replicate anywhere. The second thing, your app being optimally deployed and managed, well, that's what container management platforms like Kubernetes, Docker Swarm, Mesos, they're all about. So they're all trying to deploy your containers in a way that makes sense for you in an automatic way so that you don't have to worry about it yourself. And the third thing about all resources being available when you need them, well, that's what, to me at least, that's what the cloud is about. Google Cloud, AWS, Azure. They're all trying to give you a platform where things are automatically provisioned, auto-scaled, and available to you when you need them. So we have all the pieces. The only problem is they're not like really tightly integrated yet, but I think we are getting there. We are in the right direction to realize this dream of mine. All right. So now, what am I going to do in the rest of the talk is that I'm going to build a really simple service, and then we're going to containerize it using Docker. And then once it's containerized, we're going to push that image to Google Cloud. And then from there, we're going to create a Kubernetes cluster and run that container in Kubernetes. And along the way, we're going to see what kind of things Kubernetes provides for you for this container. And for the app, I'm going to use an ASP.NET Core application. Who are .NET developers here? OK, there's a few. Good. The reason, I know this is mostly a Java conference probably, but the reason why I do ASP.NET Core demos is that I used to work at Microsoft. And back then, this was like 4 or 5 years ago, you couldn't talk about .NET and Linux in the same sentence. You couldn't even think about it. Like, you didn't even, it wasn't something that you actually thought about it. So the fact that .NET runs on Linux, to me, is still not unbelievable. So that's why I try to do all my demos using ASP.NET Core on Linux. So that's what we're going to do. But the thing is, the example I'm going to show is basically after you build the container, it really doesn't matter what's running inside. It can be Java, it can be .NET, it can be Python, whatever. The point is not the language itself, it's the containers and what they give to you, right? So let's just take a look here. I had to, yep. So let me just pause here for a second. So I'm going to use Google Cloud Platform, and in Google Cloud, there's something called Cloud Shell. It basically gives you a Linux shell running in the browser. That way, and this Linux shell, it has all the tools that you need by default. So I'm going to use this Cloud Shell to build my ASP.NET Core application. So here I am in Google Cloud Platform. I start Cloud Shell from here. And then this takes a couple of seconds to basically find a Linux box for me and then attach that to Cloud Shell. Now I have my Linux box and my own space to build my application. What am I going to do is first .NET, command line tool to build ASP.NET Core applications. It's already installed there. So I'm going to use the command line tool for .NET to build my simple web app. So what we're going to do is we're going to say .NET. Well, first I need to create a folder for my application. So I'm going to call it Hello World ASP.NET Core. And then in here, we're going to say .NET new -t web. So this creates like a skeleton web application. And if you look at the contents, I already have all the files I need for this like Hello World kind of application. The first thing that we need to do is we need to change the program.js file. So this is the main file for my app. I want to make sure that it starts on port 8080. So I'm just going to add a line here to make sure that my app starts on port 8080. This way I can test it from my browser. So that's all I'm going to do here. So to do that, I just add like use URLs, HTTP, star, and then 8080. Sorry, it's a little bit hard to see. And then once we do that, I need to get my dependencies. So I'll do .NET restore. So this will look at my dependencies in project.json, and it will download them from NuGet. So if you're a Java person, this is kind of like getting your dependencies from Maven, basically. So we are downloading all the dependencies of my application. Once that's done, we're going to do .NET run, and this will compile and run our application. And then we'll take a look at it from the browser, make sure that it works. And that's it. So we'll use this app as like a demo app to build our container. So we're doing .NET run now. So this is compiling the application. And then within a few seconds, we'll have it running on this Linux box. And this is .NET running on Linux. I will keep saying this for a while because I really like that, you know. So I am previewing my app in the browser now. Google Cloud Shell has like this web preview feature, and now this is the skeleton web app running on Linux, and this is .NET. All right, so nothing fancy, but we'll use this app and we'll build on it as we go through the presentation. All right, so now let's talk about containers. So first, again, as I said, like I always like to answer the question of why. So let's answer why containers first. If you look at how we used to deploy applications, we used to have a physical machine, then we installed the operating system, then we installed the libraries on top of the operating system, and then we deployed our applications on top of the libraries, right? The good thing here is that we have a single physical machine, a single operating system, and a single set of libraries. So it was kind of easy to set up. But the bad thing is that there was no separation at all between applications. So anytime you change something with the kernel or with the libraries, you could break any of the apps. So that wasn't good. Then virtual machines came along. In virtual machines, the idea is that on a single physical machine, you have multiple virtual operating systems. So you're virtualizing the operating system and the libraries, and then you build your app on top of that. The good thing here is that your apps are completely separated. So if you change something in here, it's not going to affect anything in here. But the bad thing is that instead of maintaining one operating system. Now you're maintaining multiple operating systems. So it's a lot of management you have to do. Then containers came along, and the idea of containers is that you have a single machine and a single operating system, but you're virtualizing your dependencies, your libraries or your application, and your app itself. So this way, you're kind of getting best of the both worlds, right? You don't have multiple operating systems, you don't have multiple machines, you just have a single machine and single operating system, but your apps are still isolated from each other. And these containers are really lightweight, they're really easy to start, so you're kind of getting the best of both worlds. So that's why containers are big. And in terms of what is a container, it's basically a lightweight way of virtualizing your applications. So it's a way of virtualizing your applications, but the difference from virtual machines is that it's very lightweight. They are sealed and isolated, so you can have multiple containers running on the operating system, but they don't step on each other because they are separated by namespaces. And then they're very easy to deploy, so it takes like seconds to deploy. They're introspectable, so you can actually SSH into the container. You can see what's happening in there. And for me, the most important part is they're composable. So what you can have is that you can have base images that you depend on. So that's your dependency. And you can build your images on top of that. So you can layer your images. You can layer your dependencies on top of your base images. So this way, if someone gets your image, they can build on top of your image. So they can compose these dependencies on top of each other. So Docker is the main container platform that most people use, but there are others. There's something called Rocket from CoreOS that also works. And I'm sure there will be more in the future. So just to let you know that Docker is not the only one. All right, and then containers, they might look like they're something new, but at Google, actually, we've been running containers for a long time, for more than 10 years. And everything at Google actually runs in containers. So the Gmail, search, maps, even the VMs in Google Cloud Platform, they run within containers because we like the security model of containers and our whole infrastructure is optimized for containers. And this number is probably outdated now, but we launch over 2 billion containers per week. So you can see the scale of containers at Google. All right, so now what we're going to do is we built our simple Hello World app. So we're going to take it and containerize it using Docker and see how that looks like. All right, so I'm in Cloud Shell and in the same folder as before. First, what I need to do is I need to create a single DLL for my application. And to do that, I run a command called .NET publish -c release. So this will basically compile my application, compile all of its dependencies, and create a single DLL. And later, I'm going to use, from Docker, I'm going to call this DLL. So that's why I'm kind of putting it all together. In the Java world, this is kind of like creating a single jar for my application. That's what I'm doing here. I'm just putting everything together into a single file. So once we have this DLL, what I need to do is I need to create what's called a Docker file. A Docker file is kind of like a blueprint for the Docker image that we're going to run in the container. So it will tell Docker how to create the image. So we'll create the Docker file, and we'll take a look at the Docker file because it's really important. That's where we define everything about the Docker image. So we'll do that. So this created the single DLL that I need. And what I'm going to do is I'm getting into the release folder where the DLL is in the publish folder. And now I'm going to copy a Docker file that I created before into this folder. And then we're going to take a look at this Docker file. And I want to explain you what this Docker file is and what it's supposed to do. So let's just take a look. And I'll pause here for a second. All right. So this is where all the magic happens. It's kind of hard to see, but I'll try to explain it here. The first line says from Microsoft/.NET 101 runtime. So as I mentioned to you, this is in Docker, you can rely on other images, right? So here I'm relying on a base image from Microsoft. It's the .NET runtime image that I rely on. So that's what I'm saying here. Then I'm copy .app. So this means that copy all the DLLs in my folder to the app folder in the container. And then I'm setting work directory to app. So this is the app directory in the container will be the working directory for my container. Then I'm exposing port 8080 in the container. Then I'm setting an environment variable called ASP.NET Core URLs. So this environment variable will make sure that my ASP.NET Core application will start on port 8080. And then finally, the entry point, this is what happens when the container starts. I'm calling .NET. This is the command line tool to start .NET applications. And then I'm just pointing to my DLL, okay? So with this Docker file, what I'm doing is I'm declaring my dependency. So this is my dependency, the first line. Then I'm setting up my environment. So I'm copying my DLLs, I'm exposing my ports, I'm setting the environment variables, and I'm defining how it should run. So I'm defining that it should call .NET and then DLL. So with one file, I'm defining my dependencies, my environment, and how to run it, which is great. All right, so once we have this Docker file, we need to actually build the image. So to do that, we're going to use a Docker command line tool. So the Docker command line tool is already installed in Class Shell. So I'm just going to say Docker and build. And then I'm going to tag my image. It's a good practice to tag your images. So here I'm tagging it with gcr.io. GCR stands for Google Container Repository. I'm going to push this image to Google Cloud. So that's why I'm tagging it this way. So the first one says Google Container Repository. The second one is my project name. The third one is the name I choose for my container. And then a version name. So that's kind of like a good practice to do it this way. And what's happening is basically this is now looking at my Docker file and running through it. So the first step is to pull my dependency. So remember, I depend on the Microsoft image. So it's pulling that image because I don't have that image on my machine right now. It's pulling that image. And once it has that image, it will go through the other steps. This is usually takes the longest because you need to pull the whole image. Once this is done, it will go through those other steps of copying DLLs, setting environment variables. So now it's copying the DLL. And now setting up the environment variables, and now it's done. My image is built. If I do Docker images, now I should see my image built on my machine. So that's what I'm going to do next. And then you'll realize that we'll have two images. The first image is the image that I just built. The second one is the image I depend on, the Microsoft image. They're both on my machine. The third thing I need to do is I want to actually run this image and make sure that it works before I push it. So what I do is Docker run. -D means run in the background. -P means port 880. This means that expose port 880 on my container to port 880 on my machine. This way, when I hit port 880 on my machine, it goes to containers port 880. And then I point to my image, basically. So now it's running. I do a preview. And we're going to see the same app now running exactly the same way. So nothing different from outside. But the difference is now this is running within Docker. So it's basically a Docker container running right now. And I can stop the container. So if I do Docker stop, this will stop my container. So my app is not running anymore. And the great thing at this point is that I can push this image anywhere I want. So what I'm doing right now is I'm using a tool called gcloud. It's a command line tool for Google Cloud. And I'm saying gcloud docker push and point to my image. So I'm basically taking the image that I built on my Linux box and I'm pushing it to Google Cloud. I do that because later I'm going to pull this image and use it in Kubernetes. So that's the beauty of Docker, is that once you build your image, you can push it to anywhere. You can push it to Docker Hub, you can push it to Google Container Repository, and you can pull it from anywhere you want. So it really makes your code really portable. You can push and pull from anywhere you want. So we are not going to wait for this because it takes a while and we don't have that much time. But in the next step, we'll actually pull this image and work with that. All right, so we built our Hello World app. We containerized it. So let's just keep going forward. So containers, they basically help you to create like a lightweight and consistent way, actually a context for your applications to run in. But there's still a lot of things that you need to worry about in production, right? For example, if you want to have redundancy, if you want to have multiple versions of your app running, you need to take care of that. If you want resiliency, so you want to make sure that your app is actually healthy, you need to create health endpoints. If you want to scale your app or down, you need to do that yourself. If you want to deploy a new version, you need to do that. If you want to roll back to a previous version, you need to do that. So there's all these things that you need to still do, and containers don't really help for this, right? It's still your responsibility. So that's when Kubernetes comes in. Kubernetes is trying to basically answer all these questions and give you a framework to basically do all this production stuff in an easier way. That's the whole point of Kubernetes. So what is Kubernetes? It's a Greek word for governor. Actually, the right way of saying Kubernetes is Kubernetes. Everyone says it wrong because it started in the US, I guess. But it's a Greek word, and I'm originally from Cyprus, so I know a little bit of Greek. So if you don't learn anything about this talk today, just learn that Kubernetes is actually Kubernetes, okay? It tries to manage containers, container clusters. It's an 100% open source project. It's written in Go. It's supported by Google, Red Hat, and a bunch of other companies. Even though it's open source, it actually came from something called Borg. So at Google, we've been running containers for a long time. We built this internal container management system called Borg. So people who worked on Borg, they actually learned from it, and they created Kubernetes from the learnings of Borg. So even though it's open source, it's a really mature project because people actually learned from Borg and created Kubernetes. And the great thing about Kubernetes is that it supports multiple cloud providers. So you can run it on your machine, you can run it in your own data center, you can run it on Google Cloud, AWS, Azure. So it really avoids vendor lock-in. So you can run it anywhere pretty much, and that's a great thing about it. And it also supports multiple container runtimes. So you usually use Kubernetes with Docker, but you can also use it with other things like Rocket as well. So it tries to be really general and really pluggable for whatever you need to do. At the high level, this is what it looks like. So there's a master that manages the cluster, and the master has like API server, etcd to keep track of the cluster state, the scheduler and controllers. Then you have nodes where you actually schedule containers, and then the master talks to the nodes using something called kubelet. But as a user, you talk to the master. You usually use the Kubernetes API, but there's also a CLI and a user interface as well to talk to the master. And actually, as a user, you don't even care about this. You only care about the API. You talk to Kubernetes through the API, and the fact that there's a master is kind of irrelevant to you. So to set up a Kubernetes cluster, first you need to set up your master nodes. You need to choose a cloud provider. You need to provision machines for the containers. You need to configure networking. So there's a lot of steps to do if you want to do it yourself. Or you can use something called Google Container Engine that basically gives you a Kubernetes cluster with just one command. So all these things that you need to do yourself, it kind of abstracts that away for you, and then you can just use Container Engine to get your Kubernetes cluster. And other cloud providers, they also have their own container engine to make these steps easier for you. So once you, so to do it on Google Cloud Platform, this is what it looks like. So first what you do is you build your application in Cloud Shell, then you create a Docker image with Docker file. You push that image to some kind of registry. In this case, it's Google Container Registry. And then you use gcloud to create a Kubernetes cluster. So once you have the cluster, you can use kubectl. This is another command line tool to manage Kubernetes cluster. You use kubectl to schedule containers into your cluster. So it will basically pull the images from the registry, and it will schedule them in here. So in our case, we built our app here. We create a Docker file. We push our image to container registry, but we still don't have Kubernetes cluster. And we still haven't scheduled containers onto our cluster. So that's what we're going to do next in our demo. All right, so in the next one, let's just create a Kubernetes cluster that we can use. So remember, we were pushing our image to Google Cloud. So here, I already pushed the image. So if we go to container registry in Google Cloud Platform console, we should see an image for hello.net. And then if you look under there, we should see a version number 1. So this is the image that we pushed. It's already in Google Cloud. Now I'm going to use that in my Kubernetes cluster. But first, I need to create a cluster. So to do that, I'm going to use the gcloud command. So I'll say gcloud container clusters create, I think. And then I'll give my cluster a name, hello.net cluster. And then you can specify how many machines you want for your cluster. So these are the machines where I'm going to schedule containers on. In this case, I'm just using one node, but usually you need more than one node in your cluster. Then you can also specify what kind of machines you want for your cluster. So I'm using standard machines that they have, I think, like 2 CPUs or something like that. But there's a whole range of machines that you can use for your use case. And I'm also specifying zone. Zone is where my cluster is going to be. In this case, it's going to be Europe West. So with this one command, I'm basically getting a Kubernetes master. And then I'm also getting a node where the containers will be scheduled, and everything will be put together by Google Cloud. And then after like a couple of minutes, I'm going to have a Kubernetes cluster that I can work with. So it really makes it much easier than having to do this yourself. Just with one command, you get a cluster that you can work with. So I'm going to go fast forward a little bit. Actually, we are almost at the end of it. So now it showed up here. And once this spinning is done, which usually takes like a minute or two, I will have a cluster that I can schedule containers on. So that's what it takes to basically get a cluster on Google Cloud. It's pretty much the same in other cloud providers. If you had to do it yourself in your own environment, it's a little bit longer, but that's kind of like how it looks like. All right, so once we have the cluster, we can use it. So we're going to run basically what's called pods, and we're going to have replica sets and services and volumes. So I'm going to go through these and explain what they are. So this is basically the kind of the heart of the talk. What are the building blocks Kubernetes provides? Just to warn you, there's a lot of terminology that comes with Kubernetes. So this is the terminology that we're going to cover. And there's more. So this is just kind of like the basics. At the beginning, it might sound a little bit too much. But once you go through them, it kind of makes sense. And everything in here is stuff that you don't have to do it yourself. So it's actually a good thing that Kubernetes is really rich with this kind of terminology. So we'll go through these one by one quickly. At the very high level, this is what a Kubernetes cluster looks like. So first, you have your container in some kind of registry. So in our case, it's Google Container Registry. Then you create what's called a pod template. A pod is basically a single or multiple containers that you put together. So you create a template for that. And then you create something called replication controller. So you tell replication controller what you want it to be true. In this case, I want 3 replicas. So this basically says, create me 3 pods somewhere. And then what replication controller does is that it looks at your nodes. So these are the nodes that you have in your cluster. And it schedules these pods in a way that makes sense. So as a user, you don't care because it's replication controller's job to find a node and schedule your pods. And then once you have your pods running, you need to expose them to the outside world. So you create what's called a service. A service is kind of like a load balancer for your pods. And once you have your service, then people from outside world, they can hit your service. And then from their service, they can get to your pod. So your microservice in this world is basically not just your code. Your code is the container. But it's your code plus the replication controller who watches your pod and your service that exposes your pod and everything about Kubernetes basically. So it becomes a combination of Kubernetes and your container. So that becomes your microservice. So we'll go through these pieces individually now. But at the high level, that's what it looks like to you. So the first thing that I want to talk about is what's called deployment. So when you want to use Kubernetes, you create what's called a deployment. Deployment, you can think of it as like a high-level construct that basically creates the lower-level things that you need. So you create a deployment, and that creates a pod, and it creates a replica set, and so on and so forth. And I'll explain what pods and replica sets are. So let's just create a deployment in Kubernetes and see how it looks like. So here we are. We have the cluster running. And what I want to do is I want to create a deployment with the image that I just pushed. So to do that, first I need to authenticate my Cloud Shell with Kubernetes so I can run Kubernetes commands. So I just run one gcloud command to authenticate. Once I'm authenticated, now I can run kubectl commands. So I'll say kubectl, run, and give my deployment a name. So in this case, I'm calling it hello.net. That's the name of my deployment. And then I just point to my image. So this is the image that I pushed earlier. So with this, it will create a deployment. And then under the covers, it will create a pod. It will create a replica set. It will create a service. So it will create everything I need to run this image in Kubernetes. So I'm pointing to my image, and I'm also exposing the port 8080. So deployment is created. It's very fast. So if I do kubectl get deployment, I should see that I have my deployment already set up. Then if I do kubectl get pods, so I should see a pod, but then it says container creating. So Kubernetes is creating the container, so it's trying to schedule it basically. If I do get pods again, now it says running. So within a few seconds, my pod is running. And then if I do kubectl get replica set, this is the guy watching my pod. I'm going to explain shortly. Replica set is also set up. And then if I do kubectl get services, we have a service already with an internal IP, but there's no external IP because I'm not ready to expose my service yet. But they're already created for me. So with one deployment, I have everything. So now let's go through these constructs, replica sets and deployments and everything and see what we have. All right, so we went through deployment. The rest will be really quick because I want to cover them. But if it's too quick, find me after my talk and I'll explain them in more detail. So I mentioned pods and volumes. So usually you have a single container that you want to schedule, but there are some cases where you want to have multiple containers together. For example, in this case, I have a container called file puller that pulls some file from some content management system. Then it saves it to a temporary storage called volume. And then I have another container called web server that pulls that content and gives it to consumers. So in this case, I want my two containers, file puller and web server, to live together. And I want the volume also to live together as well. So I put them in what's called a pod. This way, they get scheduled as a unit. So that's what you do in Kubernetes. You can have a single container, or you can have multiple containers, or you can have multiple containers with volume in a single pod. So volumes, as I mentioned, they're storage for pod, and they can attach to many things. So you can have a volume that gets attached to a persistent disk and things like that. So we covered pod and volume. Next thing is, once you have your pods, you can label them. So labels are kind of like key value pairs for your pods. So for example, in this case, let's say I have these pods, and I have my one label is called app equals my app, another label calls phase, prod, or test, another label called role, front end and back end. Once you label your pods, you can basically access them using different ways, what's called selectors. So you can say, give me all the pods of my app using this selector, or you can say, give me all the pods of front end using this selector, or back end, or prod, or test. So it gives you a lot of ways to access your pods. And these selectors are also used to create Kubernetes constructs. So when you create a service, you use these selectors to create them. All right, so we have deployment, pods, volumes. We have ways to access them using labels and selectors. Now, the most important and I think useful part of Kubernetes is what's called replica sets. They basically help for resiliency and redundancy. So let's go through the replica set. In replica set, what you do is you basically specify what you want it to be true, and it makes sure that it is true. For example, in here I'm saying I have this replica set that's managing these pods with the selector. So it's managing all the pods that have app equals my app, and then it's using this template to create the pods. And then I want 4. So that means I want 4 pods running all the time. So replica set will keep asking the API server, how many pods do I have? If it's 3, it will create a new pod somewhere and schedule it. If at some point we have 4 pods, it will stop creating a new one. So we just basically constantly ask API server how many pods I have. If at any point one of those pods go down, or if the node goes down, replica set will recognize that and it will create a new pod. So it kind of watches your pods for you basically, so that you don't have to watch yourself. Same thing here. For example, you have a replica set with 3 replicas, and the app and the selectors are app equals demo, and color is either blue or gray. So in this case, I have 3 pods. They all have app equals demo, and the color is some of them are blue or some of them are gray. So replica set will make sure that this is true at all times without you having to worry about it. So now I just want to show you quickly that they actually work. So, oops, sorry. So what I'm doing right now is I have some pod running here, and it's being watched by the replica set. What I'm going to do is I'm going to delete this pod and see if replica set responds. So what I'm doing is I'm saying kubectl delete and pass the ID of this pod and see what happens. So once I delete, now replica set is going to go crazy, and it will, if you look at it, it says there's a new pod. You can't really see it, but it says new pod and container creating. So what happened is that as soon as I deleted the pod, replica set recognized that, and then it created a new pod and scheduled that. So this container is creating, and within a few seconds, I have a new pod running. So this is great because I don't have to worry about my pods going down. There's someone watching them for me, which is great. All right. And how does replica set know that your pod is actually healthy? There's health checks in Kubernetes. So the philosophy in Kubernetes is that it's your responsibility to tell Kubernetes that your app is healthy. And you do that in 2 ways. One is called liveness probes. So you basically create an endpoint and a port, and then you configure it with some kind of configuration. And Kubernetes will ping that endpoint once in a while with this interval that you specify. And if you respond OK, then it will say it's healthy. If you say no, then it will say it's not healthy. And then once it determines that it's not healthy, it will basically kill that pod and create a new one right away. So it uses liveness probes to determine if your pod is healthy. There's also something called readiness probes. In readiness probes, your pod might be healthy, but it might not be ready to serve traffic yet because maybe it needs to get some data from somewhere. So for that, you use readiness probes. So you define your path and port again, and Kubernetes will ping that endpoint, and then when you're not ready to serve traffic, it won't send you traffic, but when you're ready, it will start sending you traffic. So that's what it uses to do that. All right, so we basically have our pod, we have our replica set watching our pod, we have our health checks. The last thing that we need to do is basically service. We need to actually expose our pod to the outside world. So to do that, we create what's called a service. The way to create a service is basically you use a selector again. So in this case, we're saying, I'm creating a service with this label, type equals FE. So all the pods that have this label will be exposed behind this service. And the service will have a stable IP, and the client will hit the service, and then it will be round robin between different pods. All right, so let me just show you how that works. So let's take a look at our deployment. It's running, and then our pods, they're running as well. So to expose my pod to the outside world, all I say is kubectl expose, then deployment, pass in my deployment name, hello.net, and then I say -- type equals load balancer. So what will happen is that Google Cloud will create a load balancer, and then it will attach it to the service, and then the service will load balance the pods. So this way, I'm basically exposing my pods to the outside world through a load balancer. If you look at kubectl get service, we have an internal IP, but the external IP says pending, because right now Google Cloud is creating the load balancer. After a few seconds, the load balancer will be created, and we'll have an external IP that we can hit. So let me just fast forward here because I don't have that much time. So yeah, at this point, we have an external IP. So if I go to the external IP, I will see the same application running, so nothing is different in terms of functionality. But the difference is this app is running within a container in Docker, and that container is put in a pod that's being watched by Kubernetes. So if something goes wrong with the pod, it will be recreated and stuff like that. So it's basically like being watched by Kubernetes. That's the difference. All right. All right, so in the last 5 minutes, I have to go through stuff really quickly. So what I want to do is I want to just give you ideas on what exists in Kubernetes, but I won't show demos of them because I don't have time. But feel free to reach out to me after my talk, and I'll go through them with you if you want. So there's a Kubernetes dashboard by default. It gives you basically access to the pods and services and replica sets that you can use. I have a demo of it, but I don't want to show it right now because of the time. And then there are other things. For example, if you want to scale in Kubernetes, so let's say you have a replica set with 3 pods, and they're being exposed behind a service. If you want to scale up, it's basically as easy as changing this 3 to 4, and then replica set will basically just create the pod and schedule it on some kind of node. It's just one command. With one command, you can scale up and down. I have a demo, but I'll skip it. Rolling updates. This is really important. Let's say you have your app version 1 being managed by the replica set, and it's been exposed by the service. You want to upgrade it to version 2. The right way of doing that is basically to create a new replica set with version 2, and then add a new pod. This pod is being served behind the service because the service uses app equals my app for the selector. So behind the single service, you can serve different versions. And then if everything is good, you take one node here, you add one node here, you take one out, and keep going like that. And then in the end, everything goes good. Then you get rid of this replica set, and then you have the new replica set, right? So this is rolling update. In Kubernetes, this is, again, with one command, you do a rolling update, and it does this sequence of events in the right order, the right way for you, basically. So you don't have to do this yourself. It does it for you automatically. And then you can do canary deployments. So let's say you have a new version. You want to test that in production before rolling it out. What you can do is you have a replica set with the old version. You create a new replica set with the new version. You serve them behind the same service. And then if everything is good, you do a rolling update, and then you have your new version. So doing canary deployments is really easy in Kubernetes. And then auto-scaling. So let's say you have your pods running with a replica set. You can install something called Heapster that collects metrics from each pod. And then you can, in replica set, you can specify, I want CPU target to be 50%. So if the average CPU goes above 50%, replica set will realize that, and it will create new pods to bring the average down. So this way, things are auto-scaled automatically. This is pod auto-scaling, so pods are auto-scaled automatically, but also the nodes under the pods, so the actual machines, you can also set auto-scaling for them as well. So this way, you have nodes auto-scaling and pods auto-scaling automatically. So everything is really elastic, and it just works. All right, I think I'm running out of time, but just in one sentence, I want to cover these. So daemon sets. Let's say you want to have a pod. You want to make sure that you have a pod running on every single node. Let's say it's like an audit pod or something like that, where you're doing some auditing. For those, you create what's called daemon sets. This way, a pod gets scheduled on every single node. There's something called jobs. So usually pods, they run forever. They don't die unless they're not healthy. But sometimes you want to do, like, say, batch processing, where there's some kind of job, and then the jobs, you want the pod to run as much as there's job, but once the job is done, you want the pod to go away. So for those, you create what's called jobs. So they're pods basically that run as long as there's jobs, but once the job is done, the pods go away. Then there's stateful sets. So the pods are stateless usually, but if you need to create some state, because you need to have like master and slave, or you need to have MySQL with some kind of state, you can create what's called stateful pods, and these pods basically they have state that gets persisted, and then you can also specify the order of the pods, so you can say this pod starts and then this pod starts, so you can have some kind of state with pods basically. All right, and then there's config maps. These are basically configuration for your application. You define it in a central place for your app, and then the config map gets attached to your pod as a volume. So every pod gets the config map as a volume, but your configuration lives in a central place, which is nice. And then secrets, same thing as configuration, except this is for like passwords and stuff like that. You create the secrets in a central place, and then every time a pod starts, it gets attached as a volume, okay? So we covered all of this. It was really quick. I'm sorry about that, because I want to cover as much as I can, but there's more. Don't worry, I won't go through them here. If you want to learn more, kubernetes.io is the link, and this link, cloud.google.com/container-engine, is how to run it on Container Engine. This is my Twitter and email, so if you want the slides, you can just get it from my Twitter. And if you fill the feedback form, come here, and I have 3 t-shirts to give. And if you want stickers, I also have stickers. Thanks very much. If you have questions, I'll be outside answering questions. Thank you.